Hello, my name is Brian Murray. I am a PhD candidate at the University of Tromsø, the Arctic University of Norway, and the title of my presentation today is Unsupervised Trajectory Anomaly Detection for Situation Awareness in Maritime Navigation. So the outline of my presentation is as follows. I'll start out with a short introduction and tell a bit about historical AIS data. Then I'll speak a bit about what's been done recently with data-driven trajectory prediction. Then I'll move over to the essence of this paper itself with the method and results that we were able to achieve. So I'll start out with an overview of the methodology. I'll speak a bit about trajectory extraction, global anomaly detection, trajectory clustering, and intermediate anomaly detection, where we identify both anomaly clusters and transition clusters. Then I'll speak about local anomaly detection, where we actually go in and evaluate an individual cluster and conduct a top eigenvector and bottom eigenvector analysis to identify local anomalies. And we also investigate the Mahalanobis distance. Finally, I will have some concluding remarks. The Automatic Identification System, or AIS for short, was designed to aid in collision avoidance. Now what the system does is that it relays relevant ship parameters from one ship to another ship, such as position data, speed over ground, course over ground, as well as to base stations on land and to satellites. So the motivation here is that then vessels can see where other vessels are in the region, what their current heading is, what their speed is, and this can then allow navigators to gain a better situation awareness. Now, what has also been done is that these historical parameters, these ship behavior parameters, have been logged in historical AIS databases that we can then go into and gain insight into navigational patterns for a specific region and gain a lot of insight, in essence, into historical ship behavior. Recently, there has been work done on conducting data-driven trajectory predictions. So the idea here is that we can infer the future trajectory of a selected vessel based on the historical behavior of other vessels in the same region. So the idea here is that most likely a vessel will behave in a similar manner to that which vessels have in the past, and we can then use this information to then estimate the future trajectory. So hopefully this can then aid in evaluating the potential collision risk in the future. So for instance, we can conduct a 30-minute trajectory prediction using only historical AIS data, and then this can aid us in providing navigators or potentially future autonomous vessels with a form of enhanced situation awareness. So for instance, here on the figure on your lower left here, we have an example from some work done. It's published in Ocean Engineering, where you have a data-driven trajectory prediction using a dual linear autoencoder approach, where a 30-minute trajectory is predicted here and a distribution of where the vessel most likely will be after 30 minutes is illustrated here by these contours. So this has shown to have promising results, and this is all facilitated by data-driven approaches using historical AIS data. However, anomalous trajectories in the dataset will degrade the performance of the prediction algorithm. As a result, it is of interest to identify such anomalous trajectories in the dataset and then remove them before conducting such prediction. So this is a form of pre-processing, in a sense, that will then enhance the performance of a data-driven trajectory prediction. Furthermore, anomalous trajectories or anomalous ship behavior will be very difficult to predict. Therefore, it is of interest to identify ships that have anomalous behavior, such that a navigator that would use a potential system developed via data-driven trajectory prediction can be made aware of the anomalous behavior, such that they know that future prediction will not be as accurate. In general, it's also of interest to identify anomalous behavior such that navigators and other parties of interest can be notified of this. This figure presents an overview of the methodology, where first we conduct a global anomaly detection. This is facilitated by dimensionality reduction and then identifying outliers in the dataset and removing them. Subsequently, Gaussian mixture models are utilized to identify clusters in the data. And based on these clusters, we conduct an intermediate anomaly detection where we identify clusters that consist of anomalies, so entire clusters of anomalous data, as well as what we define as transition clusters. After this, we then look at the remaining clusters, and you can go into a cluster of what is defined as normal behavior and identify local anomalies within this cluster as well. So this is facilitated by conducting a top eigenvector analysis, a bottom eigenvector analysis, and a Mahalanobis distance analysis. So the first step is to identify relevant trajectories to identify potential anomalies. So what we initially do is to extract relevant trajectories from the historical AIS dataset. So based on a region of interest or the position of a vessel, as indicated here is by this green dot, we identify a region of interest in this red box where other vessels that have been within this region with a similar speed and course over ground are identified. And from this point, we then extract their trajectories for a certain time point into the past. So this could, for instance, be 10 minutes into the past or 30 minutes into the past, and evaluate the behavior of the past 30 minutes. So what one then can do is one can evaluate a new trajectory, for instance. So you have observed a trajectory for the past 10 minutes, and you would then like to compare that trajectory to the local behavior of other ships historically for the past 10 minutes. So then we can then identify if this behavior is anomalous or not. Furthermore, if we're trying to predict the future trajectory of this vessel, what one could then do is utilize this information to evaluate the data in the region and see if any vessels have anomalous behavior. So then we can remove these historical trajectories from the data set, again, in a sense, pre-processing it, and have an enhanced trajectory prediction. So the first step is to identify global anomalies, and this is facilitated via a spectral anomaly detection approach. So here what we try to do is to reduce the dimensionality of the data set so that we can then more easily identify potential outliers or anomalies. So what we first do is we utilize principal component analysis, where in essence what you do is you find the eigenvectors of the covariance matrix of the data, and you utilize this to then project the trajectories onto a subspace spanned by the L largest eigenvectors. So this is if you're then looking at the principal components or the top components that describe the most variance in the data. So for instance, here we see that the trajectories illustrated on the left figure are then projected into a lower dimensional space on the right, where then one data point in this two-dimensional plane actually describes a 30-minute trajectory, for instance. What can then be done is that we can evaluate these trajectory representations in this low dimensional space. So on the left-hand side here, we see a representation of a case study where we've then projected all of the trajectory vectors onto this low dimensional space. So here you see the first and second largest eigenvectors, or the two eigenvectors with the largest eigenvalues. And what one can then do is one can actually threshold various values by fitting a normal distribution onto the data itself. So for instance, here what we've done is we've actually thresholded all data points that are outside the 3 sigma confidence interval. So these trajectories are then marked in red here, and you see on the right hand side these are then illustrated by these red trajectories here. So here what we're actually seeing is, for instance, some that have turned around or are having very large course alterations or have anomalous speed values. So these are basically the trajectories that are deviating the most from what is defined as normal behavior for the region of interest. Now, the remainder of the data is then projected into a new space based on the principal components of the remaining data, and these are then clustered using Gaussian mixture models via the expectation maximization algorithm. So in essence, what Gaussian mixture models try to do is try to adapt a mixture of Gaussian distributions to the underlying data. And then via the expectation maximization algorithm, the model parameters are then updated to best fit the data itself, as you can see here on this figure on the right. So what then we're trying to do is go from a unlabeled data set on the left here with these blue dots to then groups or clusters of data that represent, in a sense, normal ship behavior or ship behavior that can be described. So this technique has shown to be quite effective. So here's an example of trajectory clustering that has been done previously, where you then see that these unlabeled trajectories are then clustered into groups of ship behavior that are quite similar. So the next step is then intermediate anomaly detection. So given a successful clustering, such as visualized here by the case study in the paper, we see that there are a number of clusters of behavior that are discovered. Now, what we'd like to do is then try and discover which of these clusters actually contain anomalous behavior in themselves and which represent normal behavior. So this is again facilitated via spectral anomaly detection. So in this lower dimensional space, it should be easier to then identify anomalous behavior. So here we see the projection of these various clusters in a two-dimensional space and a three-dimensional space. So what we find is that the clustering algorithm is actually able to identify an entire clusters of anomalies. So this we facilitate by evaluating the means of the various Gaussian distributions that comprise the Gaussian mixture model. And what we do is we then threshold the means. So if the mean of a certain cluster is outside the 3 sigma confidence interval for the entire data set in the subspace visualized here, then we classify this as an anomaly cluster. So here what has happened is that for the case study, we've identified this light green cluster as being comprised of anomalous trajectories, and we can actually see these trajectories on the right side here. So these are highly irregular trajectories that we can confirm are anomalous. So you can actually see them in the upper left figure as well, sort of distributed in the lower bottom section of the trajectory data. The other type of cluster that we're trying to discover is what we define as transition clusters. So transition clusters are, in a sense, anomalies of all the other clusters of regular data. So here, for instance, we can sort of even see in the data that these yellow and blue and sort of dark green clusters represent normal routes, if you will, whilst this purple cluster visualized here on the right actually consists of anomalies of all the other clusters. So there's sort of a transition between them. To identify such a cluster, however, is a bit more challenging as we can't threshold based on the mean in the same manner we did for anomaly clusters. However, the scatter of the data should be quite high for such transition clusters. So in other words, the data is actually quite more spread out, not as compact as the other clusters. So what we suggest to do is actually evaluate the trace of the covariance for each Gaussian distribution, and then threshold these trace values. So in this manner, we can then identify trajectory clusters that have a lot higher scatter. So in this manner, you can then identify transition clusters, as was done in the case study here, where then the purple cluster here was classified to be a transition cluster. So these again also consist of anomalies of all the other data, but in essence are sort of a transition between them. So once these anomalies are removed, we are left with what we define as normal behavior. So here we have clusters of normal behavior that, upon visual inspection of this case study here, seem to be meaningful. So the next step is then to conduct local anomaly detection. So here what we've done is we've actually gone in and investigated a cluster of normal trajectory in the data and gone in to see if we can find any local anomalies within this data set itself. So once again, what we do is we utilize spectral anomaly detection, and we then look at both the top eigenvectors, so the eigenvectors with the corresponding largest eigenvalues. So these in essence describe the most variance in the data, and threshold based on the 2 sigma and 3 sigma confidence intervals by fitting a Gaussian distribution onto the data itself. So as you can see here, what then happens is you are able to identify irregular behavior within this cluster itself. So for the 2 sigma interval, we have these orange trajectories, and for the 3 sigma, naturally we have fewer trajectories identified that are illustrated in red. Now, on the other hand, it's also been found useful to identify anomalies by investigating the bottom eigenvectors. So these are then the eigenvectors of the covariance matrix with the lowest eigenvalues. In these directions, actually, we should expect that the data is very compact, that there isn't that much variation. So it's been found that investigating these eigenvectors as well facilitate anomaly detection quite well, because then if you have representations that deviate significantly from the very compact structure, they're most likely trajectory anomalies. So here again, we have evaluated based on thresholding the 2 sigma and 3 sigma intervals, where you see here actually that we have sort of more erratic and more irregular trajectories than for the top eigenvectors. The top eigenvectors seem to identify more anomalies with respect to the overall speed and actually the position, where we can see here these anomalies on the right-hand side that significantly deviate in position identified, where with the bottom eigenvectors, we actually are able to discover sort of anomalies with respect to sub-trajectories in the data, where you see more erratic course alterations that are discovered by these. So here where we found that it's important to actually look into both the top eigenvectors and bottom eigenvectors, as you're actually able to discover different types of anomalies. We also did some work on trying to identify why these trajectories were identified as anomalies. So what we did is we actually looked at the eigenvectors and how much of a contribution each of them had in identifying this trajectory as an anomaly. So for the top eigenvectors here, we can see that the most important parts of the trajectory and classifying it as an anomaly were sort of at the end of the trajectory in the upper left-hand side here, and sort of towards the right, where you have sort of outliers of the entire region. So these are, in essence, areas where very little data was observed. So as a result, these trajectories were then classified as anomalies. For the bottom eigenvectors, however, we see that the algorithm is focused on entirely different regions of the trajectories, where you see more areas within the trajectory itself, sort of deviations in sub-trajectories are identified, and these then result in the algorithm defining these trajectories as anomalies. So we see that different anomaly modes are actually captured by evaluating these individually. The Mahalanobis distance metric differs from the top and bottom eigenvector analyses, as it takes into consideration the normalized projection onto all eigenvectors of the data. So in the figure we see here, what we find is a combination actually of anomalies that were discovered by the top and bottom eigenvectors, as well as entirely new trajectories that were not, or trajectory anomalies that were not discovered by either method. The Mahalanobis distance appears therefore to be quite powerful in discovering anomalies in the trajectory data. And this is likely due to the Mahalanobis distance taking into account all information in the trajectory and not thresholding after dimensionality reduction. So in conclusion, this paper presents a method to identify anomalous trajectories, and this can be used then for data-driven trajectory predictions, as well as in general identifying ship behavior anomalies. And this is done by first identifying global anomalies, then looking at intermediate anomalies. This is facilitated again by using a Gaussian mixture model. Then local anomalies are identified within each cluster by identifying the top and bottom eigenvectors, as well as the Mahalanobis distance. Please see the paper for further details, and if you have any questions relating to the paper itself, feel free to send me an email. Thank you for listening.